let's try to solve this problem here. So you have 2 point charges of 4 microcoulomb and 16 microcoulomb, and they are separated by a distance of 10 mm. Okay, so let's draw it out. Okay, so they are both positive, so I'll use red to represent positive charges. So one positive charge should be over here. I'll label it as Q1 maybe, just for easier label later when we do our substitution. Okay, then you have another charge which is 60 microcoulomb. Label as Q2, which is 16 microcoulomb. And they are separated by a distance of 10 millimeters. So 10 millimeter is 10 times 10 to the power negative 3. So do a bit of conversion here. 10 times 10 to the power negative 3 meter. Okay, a point P is at a distance of 8 mm from 4 microcoulomb charge. So from this charge, if you measure out 8 mm, you'll find point P somewhere around here, 8 mm away from Q1. Then here, the point P is also 6 mm away from 60 microcoulomb charge. 6 mm is probably a smaller radius around here. So if you find the intersect between these two circles, 8 mm circle from Q1 and a 6 mm circle from Q1, you'll find that point P will either be around here, up here, or somewhere around down here. Okay, it cannot be on the same line as Q1 and Q2, because if it's on the same line as Q1 and Q2, then the distance from Q1 to point P, sum it up with the distance from Q2 to point P, should be equals to 10 mm, but it's not the case. We know that 8 plus 6 is 14, so it's more than that. So definitely point P will not be on the same line as Q1 and Q2, probably somewhere above here. Okay, so I'll label this point as point P. Then I will label the distance as well. Okay, so this distance here will be 8 mm. Then this distance here will be 6 mm. Okay, so right now they ask the first question, the electric potential at point P. So we know that the presence of Q1 will produce an electric potential around this room. The presence of Q2 will also create another electric potential around in this room. So at point P here, there will be electric potential, which is a combination of electric potential due to Q1 and electric potential due to Q2. So we need to find both of them. So usually when we talk about electric potential, they are related to electric potential energy. So I usually will represent them by a spring, okay, because the idea of electric potential energy is very similar to elastic potential energy. So I'll draw as if there's a spring in between Q1 and point P. So this one, you can find the electric potential here to be equals to, let's don't label it as V because it's incomplete. Okay, let's label it as K Q1 over the distance will be R1P, the distance between charge 1 and also point P. Okay, there will be another spring showing that there are two charges that contribute to the potential at P. So this charge contribute how much potential to point P? It can be calculated using K Q2 over R2P. Okay, so you know that these two charges will contribute to the electric potential at point P. So if you want to find the electric potential at point P, we can write it as Vp. It will be equals to the sum of KQ1 over R1P, and also the sum and also KQ2 R2P. Okay, so K is a common K is common here, so we can bring it out, factorize it out. So we have Q1 over R1P and also Q2 over R2P. So now we are left with substitution. K is electrostatic constant, so 9.0 times 10 to the power of 9. Then you have your Q1, which is a positive 4 microcoulomb. Positive 4 microcoulomb. We need to include the sign here because we are talking about scalar value. So the sign matters to indicate the values, okay? So we have to put in the positive negative sign of the charge. Okay, R1P, the distance will be 8 millimeters, so 8 times 10 to the power negative 3. So that's R1P. Next, we have Q2. Q2 is a positive charge as well, so it's positive 60 microcoulomb. Positive 60 microcoulomb divided by the distance from Q2 to P. That distance will be 6 mm. So if we put it into our calculation and do a calculation, I believe you'll get an answer which is 2.85 times 10 to the power of 7 volt. Okay, so this value here represents the electric potential that we have at this point P over here. Okay, for question B, the work done to place a charge of 10 microcoulomb at point P. So initially there's only two charge, Q1 and Q2 in this picture over here. But now what will happen is we'll bring another charge. Let's call it Q3 then. Okay, let's call it as Q3. So we'll bring Q3 somewhere that is not inside the picture. We bring it into a picture and place it at P. Okay, so essentially the idea is we are going to bring it from infinity to point P. So the idea here, you are going to bring it from infinity, you bring it to point P. Okay, so that's the idea that they are trying to convey when they say they place a charge at point P. It was initially not there, then it's there. So it means I bring it from somewhere far away and put it there. Okay, so this one is work done to place a charge. They didn't mention it's by electric force, they didn't mention by electric field, they didn't mention by charge. So this one you consider it as work done by external force. Okay, so this one is work done by external force. Let's call it work external. And we have to specify it's from where to where. In this case, we bring the charge, which is Q3, from infinity to the point which is P. Okay, we know that work external is equals to delta U. It's from the lecture, which if you expand it, UB equals to Q delta V. Okay, we have to be very clear here which Q that we are putting in. There's Q1, Q2, and Q3 involved in this situation. But here we are interested with the charge that is moving from infinity to P. You're writing infinity to P, right? So the charge that is moving from infinity to P will be the Q that we sub in here. So which charge is moving from infinity to P is Q3 that is moving from infinity to P. So you can label it as Q3. Okay. And then after that, we have our potential difference, which we need to unpack it. The potential difference, we know that is final minus initial. So where is the final? You go from infinity to P. So infinity will be initial position, P will be final position. So final minus initial. Final it's P. Initial will be infinity. Okay, we know that for electric potential, if it's at infinity, you put in R here for this R. Let's say this potential here, you put in R, you sub in infinity, your answer will be 0. So the electric potential at somewhere infinity will be equal to 0. So essentially what's left is only Q3 multiplied by the electric potential at point P, which is what we get from A. So right now it's just a simple substitution. We take Q3, which is 10 microcoulomb, it's a positive value, positive 10 microcoulomb. You multiply it with Vp, which is the electric potential at point P. And from there, you are able to find the answer for work external. And the answer should be equal to 285 joule. So that's your work external over here. Okay, so next question. The electric potential energy associated with the 10 microcoulomb charge at point P. So now we have already bring in the positive 10 microcoulomb charge into the picture. So let's put in positive 10 microcoulomb Q3 inside here. And now they're interested to find what is the electric potential energy associated with this charge over here. So as I mentioned in class before, electric potential, they can either ask for electric potential of a certain charge, or they can ask for the electric potential energy of the whole system. So in this case, they're asking electric potential energy associated with the 10 microcoulomb charge. So they are specifically looking for the electric potential energy that is related to this Q3 over here. So we know that there are 3 charges over here. If we draw our spring, we can draw 3 springs in between this system of charges, right? There are 3 springs over here. But for question C over here, what we are interested with is only this spring and this spring only. Only these two springs that we are interested in, because both of them are connected to Q3. So we are only going to take the electric potential energy due to these 2 spring over here. So you can write it as C. You can take U of 10 microcoulomb charge. That one is Q3, right? So let's call it as U3. Okay, so U3 will be U13 plus U23. Okay, U3 is the electric potential energy related to Q3. U13 will be in between 1 and 3, this spring in particular. U23 will be in between Q2 and Q3, which is this spring in particular. So we are only going to sum out the energy due to these 2 springs. but not the third one, because this third one over here is not connected to Q3, so it's not relevant for our calculation. Okay, so if we continue and do our substitution, it will be KQ1 Q3 over R13 plus KQ2 Q3 over R13. Okay, which I believe you can see that Q3 is a common factor over here, so you can bring it out. It will be Q1 over R13 plus KQ2 over, this one is R23, sorry, R23. Okay, why do I factorize out the Q3 but not factorizing out the K? Because I want to highlight to you that if you notice here, KQ1 over R13, it's the same as KQ1 over R1P. R1P is from 1 to P is the same distance as from 1 to Q3. Q1 to Q3 has the same distance as distance from Q1 to P. So technically the first term over here is the first term over here. Okay, whereas KQ2 over R23, KQ2 over R23 is the same as KQ2, which is the same Q2. R2P is from 2 to P, and that's the position of Q3. So R23 and R2P are the same thing. So what I'm trying to say here is this value that you're trying to calculate here is the same as the VP that you are seeing here. Okay, so essentially what we can say is it's actually equals to Q3 multiplied by VP. Okay. A simpler way of looking at it is you can recall the equation that V is equals to U divided by Q. So the U of 3 will be related to the V at 3. Okay, so the V at 3, the electric potential at Q3 is the position P, right? So the V at P is equals to U of 3 divided by Q3. So from this idea, you get this equation over here, which is U3 equals to Q3 multiplied by VP. Okay, it's the same calculation as earlier. Okay, so it's the same substitution. Okay, so I believe you will still get the same answer, which is 285 Joule. Okay, so that's our answer for C. So you can see that the work done for question B is the same as the electric potential energy for question C. Why is it so? Because we learned from class that electric potential energy is actually the work required to bring the charge 10 microcoulomb work. Okay, let's repeat it. Electric potential energy of 10 microcoulomb is equals to the work done to bring 10 microcoulomb charge from infinity to the position of interest, which is P over here. So this B and BC here, they're actually the same thing. Because if you look at the definition for electric potential energy, you'll see that it's a work done to bring the charge from infinity to that point over here. So B and C are essentially finding the same thing. Okay, so question D, the total electric potential energy of the system. Now they ask for the whole system after we place the charge at point P. So now we have Q1, Q2, Q3, these three charges over here, and we want to find the total potential energy of the system. Okay, so let me simplify the diagram. There's too many springs inside here. Let's simplify the diagram a little bit. Okay, so three charges as usual. You have your Q1, which is 4 microcoulomb. You have your Q2, which is 60 microcoulomb. And you have your Q3, which is placed at point P. Q3 has a value of 10 microcoulomb. Okay, so we can think of the situation. There's three charges. We can connect springs in between all the charges because we think of the electric potential energy to be stored something like in between the spring that connects the two charges. Okay, these are imaginary springs, but it helps us understand the concept of energy easier. Okay, so this one it's U13, where it's equals to KQ1, Q3 over R13. This one is U23, which is equals to KQ2, Q3 over R23, which this one is U12, which is equals to KQ1, Q2 over R12. So we labeled the diagram already. And for this question, because they asked for the total electric potential energy of the system, I believe we have to add up every single spring that we find in this diagram over here. So it means we need to add up U13, add up U23, we need to add up U12. Okay, so expand it, you can get K Q1 Q3 divided by R13 plus K Q2 Q3 over R23 plus K Q1 Q2 over R12. Okay, so you can factorize out the K because those are common among the three terms over here. So it's K Q1 Q3 over R13 plus Q2 Q3 over R23 plus Q1 Q2 over R12. Okay, so the rest is just substitution. Okay, nothing too complicated. It's just that it's long. Okay, it's long, so it requires good attention and be very careful when you're doing your substitution. Okay, so Q1 it's positive 4 microcoulomb. Usually when the things require you to put in the sign, right, I put in the sign explicitly positive, explicitly writing down negative. Okay, even though it's not necessary to put in the positive sign, but I put it just to say that I actually have already include the sign in my substitution. Okay, so R13 is 8 mm. Okay, I'm going to add it Q2, Q3. Q2 is positive 16. Q3 is positive 10. And the distance between them is 6 mm. Okay, then lastly, I'm going to add on the relationship between 1 and 2, sorry, 1 and 2. So positive 4 microcoulomb multiplied by 16 microcoulomb. Okay, divide by the distance between them is 10 millimeter. Okay, so I sum up everything already, and then if I calculate, my answer of the total potential energy of the system will be 342.6 joule. Okay, if there's a mistake, it's probably just a calendar mistake somewhere where I substitute it wrongly, but if I do everything correctly, this is the way to do it, and you are able to determine the total potential energy using this method over here. Okay, so in this question, we go through the idea of electric potential, we relate it to work, and from work, we relate it to the change in potential energy, and from there, we see the total electric potential energy of the system. So it covers most of the aspect that I want to discuss when it goes to energy of electrostatic situation. Okay, that's it for this question. Thank you very much.